Okay, so far we've calculated heat using something called calorimetry, which involves basically just taking a hot piece of metal and putting it into some cold water kind of stuff. And we've done it for phase changes where you're taking a solid and you're adding heat and making it melt, raising the temperature, making it boil, things like that. Next one we're going to do is something called heats of reaction, and this is where we start talking about some serious heat, okay, because chemical reactions produce a lot of heat sometimes when they're very exothermic, okay. So many chemical reactions produce heat. So if you've ever had those little toe warmers that you put in your ski boots when you go skiing, that is actually a chemical reaction that takes place. And as you take your little packet of the heat warmers and you shake it up, it reacts with the oxygen in the air and it produces heat. There are other ones that absorb heat. A good example of that is like if you have a cold pack and you twist your ankle at football practice or something, they crack that little thing on the inside, the little plastic, there's a little plastic container on the inside, shake it up really good, make the reaction happen, and it starts to absorb heat. That reaction is absorbing heat. And we can calculate that as well. So we have to figure out how much energy something has for a chemical reaction, the amount of heat. And there's two methods we're going to do for that. One of them we're going to do today, and the other one we're going to do the next time when we do something called Hess's Law. So the easy one is something called heats of formation. And so these are based on a standard value for determining the heat in a reaction. And what they have to do is they have to have some basis where they can call it zero. And so the standard heats of formation, and they're written as delta H because now we're talking chemical reaction. It means a little bit different than Q, but as far as you guys are concerned, it means the exact same thing as Q. So delta H means Q, and these are the heats of formation, and that comes from chemical reactions. And the rule is, this is where their starting point is, each element in its standard state, meaning as it normally exists at 25 degrees Celsius in normal pressure, has a heat of formation of 0. This is something you're going to have to memorize. So I'm talking about iron being a solid. That's its standard state at 25 degrees in normal pressure. Oxygen, on the other hand, is a gas. Okay, that's its standard state. Mercury, its standard state is a liquid, and it just depends on what it is. But if it's an element in its standard state, you should assume it's 0. So the heat of formation of a compound is, so a compound would be something like H2O, is the change in enthalpy. That's what the delta H actually stands for. It means heat, change in heat that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard states at 25 degrees Celsius. So the heat of formation for water would be the amount of heat that's produced when you take a hydrogen and an oxygen, and you're only forming 1 mole of a compound. That's kind of the rule, 1 mole of that compound, which means that you have to actually have a fraction in front of the oxygen, and that's okay. Normally we don't do that when we balance, but when it comes to heat stuff, because you're forming 1 compound, we're going to start to see some fractions. Okay, don't panic. It doesn't mean half a molecule. What it means is half a mole. And you can have half a mole just like you can have half a dozen donuts. Same idea. Okay? And all compounds have standard values listed in tables. You'll be given them, but keep in mind, elements are 0. You need to know that. So, the heat of reaction for any kind of chemical reaction can be calculated a little bit different than what we've been doing. So before we were doing Q equals MC delta T, Q equals mass times heat of fusion. Now we're going to do it, we're going to call it, first of all, we're going to call it delta H because it's involving with a reaction. And the way it works is if you have a calculated heat of reaction, so delta H, Rxn, if it's a positive value, it is endothermic. Heat has to be added to make that reaction work. That's an easy way to remember. Heat must be added. Okay? If it's negative, that means heat is given off, and so it's exothermic. So it's the opposite, and we're going to run into that a lot when we start doing reversible reactions. If the heat of reaction is positive, when it's one direction, it's endothermic. If you change the direction of the reaction, it becomes exothermic, and it's negative. So think back to the hydrate lab when we did that. The heat of reaction is symbolized as delta H Rxn. It means the same thing as far as you guys are concerned as Q. The way you calculate delta H reaction, this is the equation. I bet that looks like a whole lot of Greek to you, because it is. This little funny looking thing is called a sigma. It means sum. That means delta, change in. But it's basically the sum of the products delta H's, minus the sum of the reactants, delta H's. Okay, so the heat of reaction is basically the products minus the reactants. Adding them up individually and then subtracting the totals of each. So the heat of reaction is equal to the difference between the sum of the heats of formation of the products minus the sum of the heats of formation. That's what difference means, of the reactants. Products minus reactants. So I'm going to give you these numbers, and I'm going to show you how to calculate it. So the heat of the reaction is the products minus the reactants. So I'm going to do them individually. Products first. Products, remember, they're on this side of the arrow. I have NO2, and I give you the number. Now notice there's 4 of them in my balanced equation. This is in kilojoules per mole. I need to account for that 4 when I'm doing this. So I need to take 4 times the 34, add it to the water. And water you want to watch out for because there's sometimes a gas too. This one's liquid. There are 6 of them, so 6 times negative 286. And literally I am going to solve that right now before I move on. And make sure you use the negative button and not the minus button on your calculator. So it's negative 1580 kilojoules. That's the product value, the reactant value. Over here, these are the reactants. NH3 is negative 46, but notice there's a 4. So 4 times negative 46 plus oxygen, there's a 7. But look, oh my God, there's no value for oxygen. Do not panic. If it does not have a value, that is a good chance, not a 100% chance, but a good chance that it's an element. And if it's an element, it's 0. So all I have is I'm going to solve this one. You get negative 184. So the heat of reaction is going to be negative 1580. That's the product value, minus the reactant value, which is negative 184. And yes, I know I have 2 negatives right next to each other, but this is the way the equation is arranged. And the fact that this is negative, that's why I put it in parentheses, so that I can keep it straight. Now, if you have a graphing calculator, I know you can just type this in. Negative 1580, use the negative button, minus, use the minus button, negative 184, and use the negative button again. And you should get negative 1396 kilojoules. Check and see if you can do that on your calculator, if your calculator works the same way as mine. Okay, so let's practice this one. Calculate the heat of reaction when octane, which is the main component of gasoline, burns. Here's your balanced chemical equation. Products on this side, reactants on this side. Heat of reaction is products minus reactants. So products, add them up. Reactants, add them up. And then find the heat of reaction. Put the products, subtract the reactants. And literally, I would do it this way. Don't do it all on your calculator. You're going to mess up. All right, so let's see if you guys got the right answer. So for the products, I have 16 times negative 396 plus, because it's the sum of the products, 18 times negative 242. And I'm going to type that in on my calculator. And I get negative 10,692 kilojoules. For the reactants, these are my reactants, 2 times the octane. And again, I don't have a value for oxygen, and that tells me that probably it's an element, and so I'm going to check. Yes, it is. That means it's 0. So I have negative 500 for my reactants. So products go here, negative 10,692 minus my reactants, negative 500. So negative 10,692 minus negative 500, and you get negative 10,192 kilojoules. This is a lot of heat. Okay, this is a lot of heat because that's kilojoules. If I had it in joules, it'd be 10,192,123 joules. 10 million joules. This is some significant heat, but then we would expect that because it's a reaction and it's burning. Okay, now this one's a little bit different, but you handle it the same way. You know, heat of reaction is the products minus the reactants. So I'm going to do the products, I'm going to do the reactants, and then I'm saying delta H of the reaction is the product value minus the reactant value. Literally, please do it this way. Don't make your life miserable because you can easily mess this up. Products are here, reactants are there. So my product is H2SO4. I don't have a number for it. Now, is it an element? No. It's got more than one capital letter. That's what I'm trying to solve for in this problem, is that value. I don't know what it is, x. Okay? If it was an element, it would be 0, but it's not an element. Then my reactants are over here. Water is negative 286 plus SO3 is negative 396. I don't have any coefficients, so all I need to do is basically add those together. And I get negative 682. And now I'm going to put this into products, x, minus reactants, equals the heat of reaction. So I'm going to erase that value right here. And I'm going to put in the heat of reaction, which was given to me in the problem, of negative 1305. So doing the algebra, I got negative 1305 equals x. Well, you know that these two together become a plus sign, plus 682. Do the algebra, negative 1305 minus 682 to solve for x. And I get x equals negative 1987, and the units would be kilojoules per mole. But if you just left kilojoules, that should be fine. Okay, so it's really important. I would literally set all this up every time when I'm doing these problems, because you can easily mess up, really easily, because we read left to right, and you're going to put the reactants before the products. And when I grade things, if you see me write P minus R minus 3, that means you didn't put them in the right order. Okay, it is products minus reactants. I would write that down every time.